Do you know how combustion engines produce mechanical work? Well, these engines work by burning fuels such as petrol or diesel. Thus, as mentioned in the previous video, there are many chemical reactions that involve the generation of gases capable of doing mechanical work. In order to quantify these changes and relate them to the changes in the internal energy, we need to understand the nature of the work a system can do. This video deals with such work. Consider a change in the state of a system, that is, from its initial state to a final state. During this change, energy may be transferred as heat or work either from the system to the surroundings or vice versa. In thermodynamics, the only type of work considered is the work done during the compression or the expansion of a gas. This is called the pressure volume work. Let us discuss this with an example. Consider a cylinder with 1 mole of an ideal gas fitted with a frictionless piston, as you can see here. Here, A is the area of cross-section of the cylinder, P is the pressure of the gas inside, and Vi, that is the volume of the cylinder. Now, if an external pressure is applied on the piston such that P external is greater than P, then the gas is compressed. Here the final volume is represented by the Vf. Then you may write the change in volume as delta V equal to Vf minus Vi. Or you may also write the change in volume as distance moved by the piston, that is L, multiplied by the area A. As pressure is the ratio of force to area, you may write the force on the piston as P external into A. Now the work done on the system, W is equal to force into distance, which is equal to P external into A into L. Or work done W is equal to P external into minus of delta V, or minus P external into Vf minus Vi. Now let us see how this expression works for both compression and expansion of a gas. Consider compression of a gas. Here Vf will be less than Vi. Hence, in the equation, we will get a negative value for the change in volume. And if this negative volume is multiplied by the negative external pressure, the resultant work will be positive. Therefore, work is done on the system, or you may say that compression work is positive. On the other hand, when a gas expands, Vf will be greater than Vi. Here the work is done by the system and will be negative. Now consider the situation where the pressure is not constant and changes in finite steps during each stage of compression. Here the work done on the gas will be given by the expression work done W is equal to minus of summation of P delta V. Now if you plot this on a graph, the work done is visible as the shaded area. On the other hand, if the pressure is not constant and if it changes during each stage in such a way that it is always infinitesimally greater than the pressure on the gas, then at each stage of compression the volume decreases by an infinitesimal amount dV. Here the work done on the gas is given by the relation W is equal to minus of integral Vi to Vf P external into dV. Now consider the expansion of a gas. Here the external pressure is always less than the pressure of the system. Thus, Px at each stage will be equal to internal pressure minus dP, which is the infinitesimal small change in pressure. While during compression, external pressure is always greater than the pressure of the system. Thus, P external at each stage is equal to the sum of internal pressure P internal and dP, the infinitesimal small change in pressure. Now, let us discuss the general equation for the external pressure applied to a system. This can be written as external pressure P external is equal to internal pressure plus or minus dP. This is known as the reversible process. Thus, a reversible process is one in which a change is brought out in such a way that the process could be reversed by an infinitesimal change at any moment. The process proceeds infinitely slowly by a series of equilibrium states. In a reversible process, the system and the surroundings are always in near equilibrium with each other. All processes other than the reversible processes are known as irreversible processes. Next, we may discuss the work done during a reversible process. Under reversible conditions, the relation between the work and the internal pressure can be written as W reversible is equal to minus of integral Vi to Vf P external into dV. By substituting the data of 1 into 2, you will get work done reversible W reversible is equal to minus of integral Vi to Vf P internal plus or minus dP into dV. Here dP into dV is very small and can be neglected. So you may write work reversible is equal to minus integral Vi to Vf P internal into dV. Now if pressure is represented in terms of the ideal gas equation and substituting the value of pressure at constant temperature in equation number 3, you will get equation number 5. Converting to log to the base of 10, you will get the final equation for reversible work. As you can see here, work done reversible is equal to minus 2.303 nRT log Vf divided by Vi. Now let us consider the expansion of gas in the vacuum, which is called free expansion. As external pressure is 0 during a free expansion, then the reversible work done W will be equal to 0. This means no work is done during the free expansion of an ideal gas, whether the process is reversible or irreversible. Next, recall the mathematical form of the first law of thermodynamics. We have previously discussed that work is equal to P external into delta V. Substituting the value of work in the mathematical form of the first law, you will get delta U equal to Q plus minus P external into delta V. At constant volume, we already know that delta V will be 0. Therefore, you may write delta U equal to QV, where the subscript V denotes the heat is applied at constant volume. To conclude, you may say that at constant volume, the heat content is same as the internal energy. Finally, we may consider isothermal free expansion of an ideal gas. By first law, delta U is equal to Q plus W. For an isothermal process, the change in internal energy delta U will be equal to 0. Thus, for an isothermal irreversible process, you may write Q equal to minus W or Q equal to minus W, which is equal to P external into Vf minus Vi. And for isothermal reversible change, you may write Q equal to minus W, which is equal to minus 2.303 nRT log Vf divided by Vi. Now, what about an adiabatic change? Well, for an adiabatic change, Q is equal to 0. Hence, the work done during an adiabatic process is the same as the change in internal energy. Here, you have learned that at constant volume, the heat content is the same as internal energy. However, all reactions do not occur at constant volume. Rather, most of the chemical reactions occur at constant pressure. During such a process, there will be changes in volume and hence work will be done. We will discuss this in our next video. With this, I will summarize this video.
Manorama Horizon. Learning made simple.